Yes. So hello all, welcome to these iitian gate classes. So here we'll be starting the strength of material solution of gate 2023 paper. Yes. So here we will be starting strength of material. As you can see, the weightage this year we will be having the weightage around 14 marks. So we have the weightage around 14 marks, like 4 questions were there of 1 marks and 5 questions were there of 2 marks. So total 9 questions were asked in this particular 2023 paper. Now, moving on to the first question we would like to take here, right? So now here, when you just consider the first question of strength of material, what they have mentioned, the stiffness of the cantilever, effective stiffness of the cantilever beam of length L, and flexural rigidity is what? Flexural rigidity is what? EI, subjected to transfer tip load is what? W. They are asking what will be the effective stiffness, right? So this is one of the very simple question. First of all, what is a whatever the tip is there at the tip, let me consider point B and here point A, right? So what you can take, what is the deflection at the point B? A cantilever beam which is being subjected to a point load. A cantilever beam which is being subjected to point load. What is the deflection formula? W L cube divided by 3EI. Once we know deflection, how we can relate to stiffness? We know that stiffness can be written as W by delta, right? W by delta. So here I can write here W divided by W L cube 3I. So what will be the answer? 3I by L cube, right? So this is one of the easiest question you will get in strength of material, right? In GATE exam. Now, so moving on to the next question. Now here when you consider this particular question, right? Now, as you can see here, now a beam is undergoing a pure bending, right? As shown in the figure, the stress versus strain diagram has been given in the particularly question. That this particular diagram is what? For elastoplastic, material, right? This particular topic, whatever the question they have given based on the graph, if you see, this graph is what? For elastoplastic bending case. Usually we don't study this particular topic, we try to study bending stress, air stress, that's it. But this is given in additional topic. Likewise, we used to study the composite beams, right? The composite beam case, where we used to find the radius of curvature of the two beams which is being attached, right, together. Similarly, here also we will be given one concept in the Gary and Goodnow, that is nothing but the elastic plastic bending case, where stress versus strain diagram, we of course we follow the Hooke's law, right? For the deriving this equation, sigma is equal to what? My by I, where sigma will be directly proportional to y, right, for the constant bending moment and moment of inertia. So here what you will be understanding, one thing, that as the basically we are moving from the neutral axis, the bending, whatever the bending stress will be there, that will be keep on increasing, right? That is the first thing. So what you're understanding, the bending stress will be keep on increasing, right? And if you just write m by I is equal to sigma by y is equal to E by R, right? So from here what you can write, and we also know that is our assumptions, right? In the bending case, what are the assumptions we have? Bernoulli assumptions, that material should follow the Hooke's law, right? Stress would be directly proportional to strain. That is what they have given the graph, right? There is a no why I'm stretching too much on this particular thing. This is very important, right? This is very, very important. So stress is directly proportional to strain, right? So it will be very linearly up to this point. Then it is behaving like a perfectly plastic material, right? If you plot the graph of sigma versus strain for the perfectly plastic material, it will be like this. Perfect plastic material, right? So if for the perfect plastic material, what is going to be happen if you just keep on applying the bending moment? So even at the neutral axis also there will be some deformations, bending deformations, right? but we generally don't consider in our case, right? For the elastic material, this question they have given for elastoplastic bending case. So which option will be correct? A will not be correct because what they have given, sigma y we are applying, so definitely extreme fiber will be subjected to what? Maximum stress. This is not the maximum bending stress, so that is incorrect. This is also incorrect, sigma y by 2. Moving on to the next question, this particular option, what you're understanding? This option, they are saying that up to some point they will be moving linearly, and then this one will be what? Behaving like a perfectly plastic material case, right? Means after basically the deformations, elastic deformation, then plastic deformation will be there, right? So this graph is also showing the same thing. What it is showing, when you read from the graph, it is saying that you just go keep on increasing this strain value, sigma will increase. So that is also happening till this c dash, c double dash point. And after that, what is happening? It is also mentioned that when the strain will become too much high, then sigma y will be constant, that is not going to vary. And that is what we are saying that. So there is a no problem in that, right? So this particular option is correct, right? But the problem is, whatever the IT professor who framed this question, they are expecting too much from you, right? They are expecting that you assume or you just thought one very theoretical case, very idealized case, where this material, if you just keep on applying more and more amount of bending moment, right? If you just keep on applying more and more amount of bending moment, let me show that this particular picture is very much clear that it will be going like this. In this option, there is no problem, I think, right? When you see this one, there is no problem. But if you just keep on applying the bending moment more and more, right? If you just keep on applying more and more bending moment, see, if there is a beam that is not practically placed, that is there in your hand, you can do anything with that beam, right? So it's a hypothetical thinking that we can keep on increasing the bending moment. More and more the bending moment will be, then what is going to be happening? Plastic region, whatever the plastic region will be there, this constant line, constant vertical line, this plastic region enlarges, right? This particular plastic region will be keep on enlarging, and moves inwards towards the neutral axis, and moves inward toward the neutral axis, towards the neutral axis, until the condition shown in the figure is what? This particular figure which I am drawing, that is being shown, right? That is a idealized picture, right? That means if I further increase the bending moment, then what is going to be happening? Try to analyze. This may take a shape of like this. Further you are applying the bending moment, just like I can say the value infinite, right? You keep on applying the bending moment, keep on applying the bending moment. In such a case, your whatever that's again very impossible to believe that the neutral axis or whatever the neutral fiber will be there, that is also going to be deformed. Again, I'm saying there is no correlation with the practical conditions. You can never have this condition in reality, but they just want the imagination from you. That's why they have given the this question in MSQ, right? So C will also be correct. So please check it out whether you are getting this question properly or not. Any doubt? Can we move to the next question? C and D both will be correct for this case. Yes. Shall we move to the next question? Now, so when you just think of the next question, what they have mentioned. Now, in this question, they have given very clearly in question number 26, what they have given. They have given the principal stresses at a point of a solid material, right, is being subjected to 70 megapascal, minus 70 megapascal, and 0 megapascal, right? The yield stress for the material is what? 100 megapascal, right? The yield stress for the material is what? 100 megapascal. Which prediction about the material failure will be correct? Now, so what will be the correct option? You try for this. Now, when you think of this particular question, the principal stresses they have given sigma 1, that is 70 megapascal, sigma 2 is 0, sigma 3 is what? Minus 70 megapascal, right? The maximum normal stress theory predicts the material fails. So, what is the according to maximum normal stress theory? Maximum of, according to maximum normal stress theory, maximum of mod sigma 1, mod sigma 2, mod sigma 2, that should be, you know, that should be if this any three values will be exceeding the sigma yield value, right? Then we say material fails. Just check it out whether 70 megapascal is exceeding this yield stress value or not. Whether it is exceeding, no. So whatever the maximum normal stress theory is there, it is saying that 70 is less than 100, so material is what? Safe, right? So this is incorrect. Which option will be correct? C will be correct. Just check it out according to maximum shear stress. According to maximum shear stress, according to maximum shear stress, what we can write? Maximum of sigma 1 minus sigma 2 by 2, sigma 2 minus sigma 3 by 2, sigma 3 minus sigma 1 by 2. If that is basically exceeding sigma yt divided by what? 2, then we say that that is obviously what we are writing, tau yield. Then definitely what we can say, the material is going to fail, right? So for this case, what we can write? We can write here the maximum of sigma 1 minus sigma 2 by 2, that is 70 minus 0 by 2, that is 35. 70, that is 0 minus 70, again that will be 35. 70 plus 70, because sigma 3 minus sigma 1, so minus 70 minus 70, 140. 140 by 2, that is 70, right? So whether this value is exceeding sigma yt by 2, that is 100 by 2. So when you see that 70 is what? Exceeding 50, so material will fail. This particular material is safe with respect to normal stress theory, but with respect to shear stress theory, it will fail. So if I'll ask further this question, which will be giving you the highest factor of safety, which is giving you the more alarming conditions in both the theories of failure, the next question is over. But I'm asking, if you just think of the another question, which one will give the maximum, which one will give the maximum factor of safety, then what you will say? So definitely, which is going to predict, you know, failure of the material, definitely that will give the basically what? Least factor of safety. So normal stress theory for this case will give higher factor of safety than factor of safety which is being given by maximum shear stress theory, if at all material has to be in the safe limit, right? So this is what the discussion about this question, right? Now when we move to the next question, now when you just think of this 27th question, which of the following plot shown in the figure basically is or are, this is MSQ question representing the condition for plane stress case, right? So for the plane stress case, basically what we can have, for the plane stress case, what we can have, always this is basically what sigma x. Suppose for example this is sigma x, this is what sigma y, this is sigma y. So when you just draw the Mohr circle for this case, in any of the cases, right? So whatever the complementary shear stress will be there, what is the complementary shear stress? This tau. Suppose if I'm applying tau value on any of the phase, y phase or x phase, what you are understanding, this tau and this tau will remain same, right? So if I draw the plot, a is what sigma x and tau. According to Mohr circle, this will be a sign convention, that will be minus because anti-clockwise, and this will be clockwise sigma y and tau. So if I plot it somewhere, I'll be getting what a, and I'll be getting what b. So if I join together, I'll be getting what plot, maybe something like this. Why I am drawing this graph, this Mohr circle, trying to understand. This is tau, this is sigma, right? Understand one more thing in this case. What you need to understand, this whatever the tau value is there, right? Whatever the tau is there, this coordinates, this tau will remain same. So this height will remain same, right? So Mohr circle will always be symmetric about the x-axis. It cannot be unsymmetric about the x-axis, because when you see that here, when you just in any of the cases, what you are getting here, tau 1, here will be getting what tau 2, because see the height difference is there. Some height, basically what here the height for the point A and point B is what different, the y-axis, right? So what it is showing, your material is being subjected to tau 1 and tau 2. That is incorrect, because to satisfy the couple equilibrium, right, the tau has to be remain same, right? Magnitude has to be same, direction can be different, right? Obviously direction will be different for to satisfy the couple equilibrium. So whatever the unsymmetric circle is there, that is absolutely wrong. Here also one tau is there, tau 2 is what 0. How it is possible to maintain the couple equilibrium, right? So this option will be correct and this option will be correct. So m1 and m3 will be correct. Again m3 will also be correct, right? Don't think that it is a case of uniaxial state of stress, right? Again I am showing you right here, the value can be such a way that it can be the possibility that we'll be getting the circle just like a uniaxial state of stress also, right? Something like this. For this also sigma x comma 0, but this case is also possible for this based on the values, right? So both the answers are possible. All of you are getting my point, right? Now when we move to the next question, yes, in this particular question, what you can understand. Now, this is basically a beam of length L, whatever the beam is there, which is having a length L, is loaded in the XY plane, and it is being supported by, it is being applied by the uniformly distributed load, and there is a concentrated load which is going in the negative Z directions, like this, right? What they have been seeing, the resulting bending moment distribution about the y and z axis are shown in the figure by my and mj, right? So it is one of the very simple. First of all, whatever the distribution load is there in a cantilever beam, it is there in the vertical plane, right? Yx, that is the vertical bending moment diagram if you draw it. So according to vertical bending moment diagram in xy plane, if I plot, xy plane means what? You are taking the moment about which axis? Z axis. You are taking the moment about which axis? Z axis. So what is going to be happening? Everyone know that this will be the plot for the bending moment diagram, and obviously that will be the bending moment about what? Bending moment about Z axis, because it is there in the xy plane. What is the perpendicular plane? Z. Whatever the perpendicular axis will be there, about that axis the bending moment will be happening, right? Now some of you might be thinking why the slope is like this. If you see the other option, right? So here definitely there is a what? Hogging bending moment is happening at any point of time. If you just take bending moment at any xx cross section, what xx distance, so what you will be getting? This is W Newton per meter. So W into x minus into what? X by 2. So this distribution will be what? Parabolic distribution, right? This particular distribution is what? Parabolic and negative value, right? So minus W into L square by 2. So which option will be correct? From here itself you can just identify. Moment about z axis will be what? This one, right? B option will be correct. Now some of you might be thinking, sir, what about B option? See, in the moment when you just think of cantilever beam which is being subjected to a point load P, the movement will be happening. Which particular plane is basically what? Showing this load or bending? In which particular plane? You think of what? X and Z plane. In XZ plane, whatever the XZ plane is there, in that only the bending is happening. About which axis? About Y axis. So what about bending? Whatever the bending moment about the Y axis, that is a what? If you take any section XX, what you will be getting? What you will be getting? That is a sagging bending moment, just like a tip load, vertical, right? Sagging bending moment you will be getting, right? So that is going to be P into L. So what is the answer? And that is also linear, because at any section, if you just consider the bending moment, that is P into X. That is a linear variation. So which option will be correct? Obviously this. B will be correct, right? This is a horizontal bending moment diagram. This will be the vertical bending moment diagram, right? Getting my point or not? Now, when you think of the next question, yes, a thin wall case. This is basically a complete extension of GATE 2008 mechanical paper, which is being conducted by ISC. In that paper also, they have clearly mentioned one hanging thin cylinder, right? And there they have mentioned, right, how the basically hoop stress and longitudinal stress at a particular point, number one here, or number one here and number two here, right? So this particular graph is testing that only, nothing much about this question, right? You just think of this. Always remember hoop stress, whatever the formula we are adding, PD divided by 2T, this P will be the local pressure. Longitudinal stress will always be developed when the pressure will be acting at the ends of the cylinder, right? So pressure at the ends. It is irrespective of the particular local value, right? It will directly depend on what? Rho gh. This value will be fixed. It will not be vary with respect to the height, because suppose we want to calculate at point number one. What is the point number one? What is the longitudinal stress at the point number one? Again, the formula will be rho gh d divided by 40 only. If you want to calculate at 2, longitudinal stress, once again rho gh d divided by 40. Whether any changes will be there? No. About the longitudinal stress, no changes will be there at point number 1 and point number 2. It will be independent of the height, right? So what we can write from this, what we can conclude, that whatever the sigma 2 will be there, that sigma 2 will remains same, right? And whatever the hoop stress will be there, that is going to be vary. Whatever the hoop stress will be there, that hoop stress will be linearly vary, because you can see here P, right? At point number 1, what is the pressure? That is a rho gy. If you just want to calculate at point number 1, what the hoop stress at point number 2? That is rho gh d divided by 2t. So it is vary, right? So it is going to vary. Then what we can just conclude from here, which option will be correct? Sigma 2, what they have given in the problem, magnitude of the, see, you have to read it very carefully, right? Magnitude of the axial wall stress, that is sigma 1, will remain constant with respect to height. And what about sigma 2? Will vary linearly, right? At the top, that is 0, and it will keep on increasing with respect to height. So which option will be correct? Sigma 1, that is according to here, A option will be correct, right? Sigma 1 will be constant and sigma 2 will be varying linearly. At a distance h by 2, they will intersect. The value will be same, right? So it's a purely extension of the GATE 2008 problem, right? There is nothing much in that. Now, just think of this particular problem. Uh, Here in this question, there is a bars in connected in series, right? The bars connected in series, this particular case, two bars connected in series. Now we will be not going into the details of this, right? You can see the other YouTube videos where we have discussed about the thermal stresses. There you can watch very carefully. We have discussed the cases of all these possible scenarios of generation of what thermal stresses in the what in the bars, right? Subjected to the maybe thermal loading or mechanical loading. Now here in this question they have not mentioned anything about the external load, right? They have not mentioned anything, so it's purely the concept of thermal loading case. So only thermal stress will be developed, right? A cylindrical bar P and Q of identical length of P, length of Q is same, the radius of P, radius of Q is same, composed of linear elastic material, right? That means Hooke's law will follow. The Young's modulus and coefficient of thermal expansion of Q, E of Q is 2 times E of what? P. Coefficient of thermal expansion is what? 2 times coefficient of thermal expansion of P. The bars are held between the two rigid support. That means that is not the flexible support. That will not gonna yield. So there will not be any yielding possible at the support. So total deformation will be 0, right? Now, what they are mentioning that temperature is raised by delta T. Assume that the stress in each bar is homogeneous and uniaxial. Denote the magnitude of the stress P and Q, basically by sigma 1 and sigma 2. So now, when you just think of reaction forces, reaction will offer. When you try to increase the temperature, right? Both the bar, what it will do? It will try to push this particular support. The support will say you go back. They will offer some kind of resistive force, right? This resistive force, if you just do summation of forces in x direction equal to 0, what you will be getting? If you just do summation of forces in x direction, that is going to be 0. So what you will be getting? Rp, that is equal to Rq, right? What is Rp when you just consider force, right? That is a sigma p into area, right? Area of P. Sigma Q into area of what? Q. Area will be what? Pi by 4d square. But they have clearly mentioned that the diameter will be same, radius will be same, they will cancel out. So sigma P, that is denoted by what? Sigma 1. This will be equal to sigma 2, that is being denoted by sigma Q. So one option D will be correct. That is stresses will be, thermal stresses will be same, right? If I apply the load also, right? In that case, that is not the equal case scenario, right? But here they have not given any intermediate or any external load, so that is going to be 0, right? The next thing will be whether interface at P and Q, that is, if I just say this is A, this is B point and C point, we need to find deflection at point B. And according to our sign convention, if it is going in this direction, positive x-axis, that means what? Whatever the deformation is there, that is towards the right side. If it is moving towards the negative x-axis, that means what? The whatever the interface will be there, that will move towards the left side. Now let's see the possible scenario. What we need to find? The total deflection at point B, right? So what is the what we can write further? The total deflection will be 0. Total deflection means what? Deflection of AB member, deflection of BC member will be 0, right? Further, what we can write? Further, what we can write? Now, here when you just think of total deformation, delta P plus delta Q is 0. Now total deformation will be there because of what? Because of mechanical deformation, because of thermal deformation, right? Total deformation will be consists of two things. So when you try to increase the temperature, then what will happening? Alpha into delta T into L of P will be there. That is a positive, that will increase, right? But because when it will try to increase its length because of the thermal deformation, it will try to increase its length like this. Then second bar, the bar Q, what it will do? It will offer some kind of resistive force. He will say that you just go back, right? So because of that, resistive force will be developed, right? So what we can say, and the resistive force I told you that is being same, right? So what we can write? Minus reaction forces, the length RL divided by what? A, that is a mechanical deformation. Everyone know that. This is EP, AP, length of P. This deformation plus further what we can write? The total net deformation, alpha into delta T into L. Then what we can write? Of Q minus R L Q A Q E Q. that is equal to 0. So what we can have the value? We can have the value here. See, length will cancel out from all the sides. Area, we can take it as AP, that is equal to AQ, that is equal to A we can take. And EQ is mentioned as what? 2 times of AP. Alpha of Q, they have mentioned what? 2 times of alpha P, right? In the problem, what they have given? That is what they have given. So here we can write alpha delta T plus 2 times of alpha delta T. R length is going to be same, area is going to be same. So here area I'm multiplying here with this A, right? So here what we can have. Now, when you just think of RL divided by AE, so here L already cancel out. So E value, I can take EP value as E, then EQ value will be what? 2E, right? So plus R divided by 2E. So here I can calculate R value as 3 by 2. That is going to be 3 alpha delta T into area. So here I'll be calculating it as alpha delta T A into E. So this is what the reaction forces we are getting, right? Deflection at interface. Deflection at the interface, if you just think of, then what we can write? We can write like this. Suppose, for example, so what we can have? Alpha into delta T into L minus RL divided by what? A. L, I can take it at outside. So alpha delta T. R, what is the value of R? 2 alpha delta T AE divided by AE, right? So if you just calculate, this will cancel out. So minus L alpha into delta T, right? So what is the value of the negative? What is the meaning of negative? Negative means this interface will move towards the left side. This will be the net deflection at the interface, right? So A option will be correct. Getting my point? A and D will be correct for this question. All of you are getting my point? Yes. Now, moving on to the next question. Again, this is one of the very basic and very simple question they ask in mechanical strength of material. And if you just think of this question, a cylindrical bar, you might have calculated already the deflection formula, right? What the deflection formula? Because of the self weight, everyone know that. That is WL divided by 2E, right? All of you might have done this calculation, but this time they ask the elastic strain energy. So that is also, we know the formula, right? Pxx whole square dx at any section, whatever the load which are acting, divided by 2AE from 0 to L. So if you just calculate Pxx, what is the Pxx formula? How the, see, because of this value, this much of whatever the beam part is there of the length x, it will try to apply some kind of load value, right? And what is the load value? W, right? What we can write? Rho g area into x. What we used to write? Mg, right? Because mg, because of this x part, it will try to pull this in the into the what? Downward directions, right? It will try to pull this part, whole beam, in the downward directions. So what we can write? This will be the load which are acting. This gamma g we can replace it by what? Rho g we can replace it by gamma into A into x, right? So here if we just put into this formula, so what further we can write? Gamma square A square divided by 2AE x square. What is the integration of x square dx? 0 to L. X cube by 3, 0 to L. So this will be L cube divided by 3. So L cube divided by 3. So gamma square A L cube divided by what? 6E. So what is the strain energy answer? Gamma, what is the rho g? Rho is what? 2700. G is what? 9.8. Don't take 9.81. whole square into what? Area. What is the area? Directly they have given 10 meters square. And length, what is the length? What is the length, my different? If you just take the length 5 meter, 6e, what is the e value? 70 gigapascal. 1 gigapascal will be what? 10 to the power 9, right? You just try to calculate in Newton meter, right? So if you just do the calculation, you'll be getting what? 2.08 joule, right? Just do that calculation whether you're getting or not. 2700 into 9.8 whole square into 10 into 5 divided by 6 divided by 70 divided by 10 power 9. Two AE, right? Area we already know 10 meters square, that we already kept. Length cube, right? This will be your cube. So here if you just calculate 27 into 9.8 whole square into 10 into 5 whole cube divided by 6 divided by 70 divided by 10 power 9. So 2.083, but we have to round off to two decimal places. So 2.08 will be correct. Right. Now moving on to the next question. This question is quite again very simple. Now the cylindrical shaft of having the length 1.5 meter having the diameter 100 mm is made up of linear elastic material, right? That means Hooke's law for the sail loading case, that will also follow the linear relationship, just like for the normal load we have, right? So Sayer modulus, they have given 80 gigapascal while operating at a speed of 500 rpm. Angle of twist they have given it as 0.5 degree. The power which is being transmitted by the shaft will be how much? So very first of all, for the power transmission, we should know 2 pi nt by 60, right? That is a formula that we know, right? Now, first of all, we need to calculate T. So T by J, tau by R, G theta by L. So these things, if you just correlate, what you will be getting? G theta J divided by L, right? So from here, you will be calculating 80 into 1000, that is a megapascal. Theta will be what? 0.5 degree, that is pi by 180, that will be in the what? In the radians, right? Because except sine or whatever the trigonometric function, that theta should be what? Always in radians, right? J will be what? Pi d power 4 divided by what? 32. Length will be what? 100, 1500 mm, right? So if you just calculate T value, let me calculate 80 into 1000 into 0.5 into pi. But here pi value you need to take care of 3.14. Don't take 3.144, something like that, right? If you just take into the calculator, it will be 3.141592654. That we don't want to take it because that will be out of the range. So if you just take only 3.14, so here you can write 80 into 1000 into 0.5 into 3.14 square into 100 to the power 4 divided by 180 divided by 32 divided by 1500, right? So that will give the values in Newton meter, right? Directly I'm writing 4564.629 Newton meter. 4564.63, right? 629 Newton meter, right? So now if you just put the formula 2 pi n is what? 500 rpm. 4564.629. So what you will be getting the value? 5 into 500 into 4564.629. So you will be getting the answer as 239. That will be the correct answer, right? Now, one more thing is there. Some of you might have confused the angle of twist across its length, right? Do not confuse with that word, right? Don't think that it is given it as Sayer angle, right? Some of you might have confused, and they might have used the formula r theta by L. This is incorrect. Directly angle of twist only we have to take for our considerations, right? So I think we have discussed all the problem regarding this strength of material. Okay, guys, thank you.